Hello, everyone. Thanks. I want to thank the organizers again for putting on the conference this year again. It's great to be back. Today I'm going to be talking about how we can accelerate neural networks, deep neural networks. I know this crowd's not that into it, so don't throw any rotten tomatoes at me. Using theory from signal processing. So these are all GIFs, but I made it into a PDF for simplicity, but you get the point. So, deep neural networks are really good at a lot of specific tasks. Right, so on the top here, we have like a segmentation task of like a heart, some sort of mass they're trying to identify. This is from Google DeepMind's AlphaFold. It's actually a GIF of the algorithm learning how to fold this protein. It's actually pretty cool if you see it in real time. And obviously a self-driving car. Typical technologies we think of when we think of these things. Right, but they also have their disadvantages. Right, so one disadvantage is they require a huge amount of data. They require you to label your data, because supervised learning is probably 98, 99% of what deep learning is now. And so if you don't have enough data or you don't have a diverse enough data set, they're very susceptible to overfitting. Right, so some things you can do, obviously you can transfer your knowledge from one task to another. That's probably the most common one to avoid this. And there's some other ones as well, data augmentation, making more data out of less, and some other tricks that you can do. And so recently, as a side note, we recently worked on how you can actually have deep networks learn on about 30 samples or so total. So another common disadvantage of deep neural networks is they take very long to train typically. And so we're talking like hours minimum, depending on the task, of course. We're talking hours to sometimes even days or weeks. And it's even more for like reinforcement learning tasks and things like that. Once again, transfer learning can easily used to solve that, as well as normalization. You can normalize your inputs or normalize your internal layers of the network. They also have millions at least tunable weights. Now that some of the like VGG16 has 138 million tunable parameters. It's massive. And most of the ones like ResNet, your ResNet 50, have around 20 million parameters that you have to tune. So once again, transfer learning and some other common techniques are used to deal with this massive amount of parameters. And so this is all, has to be put into memory and has to be, tuned while you're waiting for your algorithm to converge. And so another common problem is when you're training deep nets is that it's often task specific. So if you go read online and you say, all right, I have this task, I want to have a deep net learn on this task, my task that I collected the data for, you're going to get a bunch of different answers. And of course, there'll be some standards based on the most recent techniques, but you probably are going to have to test different algorithms and different hyperparameters for your specific task. And of course, there are hyperparameter tuning algorithms out there, and also stack exchange. So what I'm here to talk about today is like how there's this current trend in deep learning where we're making everything more complicated. We're adding more layers, more different tricks, and brittle optimization techniques so that our network converges. But I'm here to talk about a different alternative route to see maybe we can accelerate them and make them more robust in other ways. And so this current trend of big, more elaborate, more power-consuming networks, it's not only good. It's not good because obviously we talked about this earlier. It takes a lot of power to run these networks. Everybody needs a GPU. They take a lot of power. Edge technologies are becoming more prevalent. You're not going to have, how are you going to put a 138 million parameter network onto an edge technology? You can prune it, you can do other things to it, but if you're going to do that, why even have the huge network in the first place? So here we take a different approach. We say, okay, so there's some signal processing out there. There's a very rich field of how do you compress information and encode it down to smaller space? Right, so compressed sensing came out in about 2005 and talking about, all right, if you have a signal and you want to compress it, obviously there's many different compression algorithms out there, JPEG, it's a very rich field. But compressed sensing is actually an interesting one because not only is is it's basically just a random sampling array. So it's very dumb encoding to get down to the encoding, but then when you go back, you can just have like a sparse solver go back. So we actually showed an LCA algorithm is more robust and can go back faster than most other algorithms for the reconstruction. So basically what the idea for compressed sensing is, you have some image X or some signal X, right, sparse, so most of the white parts represent zeros, so most of it is 0, very sparse. And so that's important for the math. I'm not going to go into it, but the signal has to be sparse for this, and there's other ways to make it sparse. And so basically what you do is just take a random array, normalized or initialized with random values taken from a normal distribution. And so basically if you do that, the columns of the array, or the rows in this case, each row will basically be like approximately orthogonal to the others. So basically what you've done is you've basically created a basis where they're basically orthogonal to each other. And so you just basically sample the signal with this sampling matrix. And so there is hardware implementations out there now where you can actually, a physical instantiation of this where it's called a single pixel camera, and you can collect images in this way. So what are the sorts of advantages to doing this approach? So one is it's easy. You can just encode it. You don't need to have any special math to do it. All you do is have like a random sampling array. Another one is that the measurements you get from it, Y, right? So I'm going to get this many measurements back. They're actually said to be democratic. And so that just means like they're robust to noise. Like none of these measurements is more important than the others. So they're very good at graceful degradation. And so reconstruction is cool. That's what's typically used for compressed sensing. But also learning is cooler. So basically just the fact that you can reconstruct this signal based on the compressed encoding means that the information must be in there somewhere. So why not just learn from that and send it to a neural network? And I'll go quickly through this. And of course, this is not a new idea. People have been trying to do this for a long time. Here's just some of my favorites, recent approaches. And of course, there's extreme learning machines and echo state networks and things like that also do something similar. And so our method, we just take the last feature map layer and we compress that using a random sampling matrix. And so what we tried to do is this is like the amnesty of RL. You got to have this in there. We tried it on Pong. These are some of our earlier results. And so the max score is 21. So basically, the agent is awarded based on what the score is relative to the opponent. So is it negative 21? So the opponent got 21, you got 0, or is it 21 and you're going to get rewarded because you got 21 and the opponent got 0? And so basically, we just chose an arbitrarily simple network. This is not a named one; just made it up, arbitrarily simple, just for our experiments and just to show how this is able to do better than what we have now. And so here's the network. And then we add in this basically this random projection layer on the feature maps. And so if I sample down, here's basically the sampling rate and the time in minutes to win the game as a function of the sampling rate. So basically at a 0.5, we have about half the time, and this is the control network. Let's see. And so this actually did twice as fast as the control network, and also when we added group normalization from 2018 and global average pooling into the network. So it's better than pretty much state of the art with a simple network. They're not able to learn that well on simple networks, and so why can't we use this to help it make it smaller? And we also added a trainable layer in the place of this random sampling matrix just to make sure, and it did a little bit better than the control, but it still did worse than the compressed version. And so here's an example of the runs we did. So here's a 0.5. It goes straight up to that's pretty much the max score it can get, nails the solution. And here you see the control network with group normalization and global average pooling takes a very long time to get up there. It gets up close to it pretty quickly, but then goes straight up. It doesn't really get up there. And so then I'll wrap up real quick. So we did this on MNIST as well. We wanted to see what is actually happening. And so we put the output, so we did a global average pooling took out the fully connected layers of AlexNet, put global average pooling, and then basically what we did was we put this compressed layer at the output. Sounds crazy, but it's really not. And so what that did was it acted as a regularization. And so we call this network fully convolutional because all we used was convolutions. We didn't train any fully connected layers. And so when this happened, these are representative samples. So this is from layer 3 of the weights. And so here's our network with the compressed output layer. And the weights are actually much more sparse. And this is just an average of them, an average of layer of the. This is basically like an average example. So some are more sparse, some are a little bit less, but most of them are actually much more sparse than the control network. We see most of, it's a fatter distribution, and also it peaks. If you look at the y-axis, it peaks higher. So we actually made a much more sparse network. And so that's all I have today. Thank you.
Thank you, Michael. We have time for probably one burning question. Looks like everyone wants to go for the break.
The initial motivation or presentation suggested you were looking at the sensor side of it. Did you try replacing the first stage of your network with these random setups instead?
Yeah. I will mention this is an ongoing research, and that's actually part of it. These are some of our earlier results. And yes, we're very interested in that, especially since they make sensors that take these measurements. And I will say the results they're promising at this time.
Okay. Thank you, Michael.